Hi everyone, my name is Tianqing Su. Welcome to my presentation. As the world becomes more digitalized and data-driven, everything is going to be connected. We want the heavy machinery industry to be part of it. Today, I want to introduce our project, Intelligence Fleet Management for the construction site, and show you one of our research on real-time estimation of IEEE 802.11p for mobile working machine communication with respect to delay and packet loss. This research is a joint work by Yusheng Xiang, Dr. Christina Brach, Xiaole Liu, and Professor Marcus Gaiman. Currently, because of lack of cooperation, the efficiency of working sites is quite low. Almost everyone has the experience that waiting in a congested traffic because the reparation of the road. This causes huge economic loss, so that we proposed the intelligent fleet management. With the Internet of Things, it introduced to solve the cooperation problems among the machineries. The information about current positions, speeds, tasks, and destinations are exchanged periodically between each individual mobile machine. Since the kinematic information and intentions of other nearby vehicles are known, more construction machines can be invested on site, and they can work more intensively and efficiently. This is a use case of vehicle-to-everything technology, the so-called V2X, on construction sites. Currently, there are two commonly used technologies for V2X, namely Wi-Fi-based network and cellular-based network. There are always discussions about which will be the dominant technology in the future. In our use case, we choose a Wi-Fi-based network for our first version. First of all, because it doesn't rely on infrastructure compared with the cellular network, where a base station is necessary. This consideration is quite essential for construction sites, since they are often located far away from urban centers and might fail to find a base station nearby. And secondly, while network operators charge users for their cellular network usage, the usage of the 11p frequency is free of charge. Wi-Fi-based network has also some weakness, such as short communication coverage. But this is of little importance because of the limited size of construction sites. 11p suffers from high delay and packet loss when the channel load is high. This is due to the contention behaviors specified in the MAC layer. In the next section, we will further explore the performance of 11p, focusing especially on how it would be affected by an increasing number of nodes. First of all, let's look at the network model briefly. In the physics layer, we choose to use the log distance path loss model. In the MAC layer, transmissions are scheduled on a single channel by CSMA-CA. The algorithm defers the access attempts using a random backoff time. Only when the backoff timer comes down to 0, the user is allowed to access the channel. We use NS3 to simulate the transmission performance. The parameters are listed here. The safety-relevant messages sent by 11p have different names in Europe and America, namely CAM message and beacon. Both are periodic broadcast messages which contain safety-relevant information such as position, speed, acceleration, etc. As specified by protocol, the message's payload and header field are modulated with different schemes and have different immunities against noise and channel fading which means that they can be received within different ranges. In this way, we define transmission range and sensing range as the successful reception limit for payload and header, respectively. Under our simulation parameter, the transmission range is measured to be 115 meters, and the sensing range is 175 meters. Once two transmitters are more than 175 meters apart, they cannot sense each other, so they may send packets simultaneously, without differing their access requests. In this case, they are called hidden nodes. Multiple packets may collide at the receiver, which is visible and connectable for both hidden nodes. The interference from the overlapping transmissions results in reception failures. Our first simulation scenario is to evaluate the impact of hidden nodes problem on the vehicle network. A total of 80 neighbor nodes are equally divided into two groups and are distributed on both sides of the transmitter and receiver pair. 12 simulations are executed with the distance between the two groups of neighbors increasing by 20 meters, from 0 to 220 meters. When the neighbor groups are hidden to each other, which means in this area, the transmitter in the middle, whose performance is denoted in blue, suffer fewer collisions, less mean delay, and less packet loss, because more idle channel is released due to overlapping transmissions among the hidden nodes. In brief, the transmitter benefits from the existence of hidden nodes. Although the NS3 can simulate the V2X performance regarding the delay and the probability of lost packets, we still need a quick estimation method so that the onboard ECU can obtain the V2X performance in real time and evaluate the plausibility of V2X data. Therefore, we built an analytical model to quickly estimate the network performance. The contention behavior due to CSMA in the transmission and sensing ranges should follow their corresponding rules, which largely depend on the number of neighbors. In other words, two key factors of communication performance for each individual nodes are user intensity and distribution of neighbor nodes. Therefore, we introduce the following model. First of all, we define the area within the transmission range as the first cluster, and the area between the transmission and sensing range as the second cluster. We generate a lookup table for each of the clusters in advance, which contain a set of crucial performance indicators, namely packet delay probability, packet loss probability, and mean delay, in relationship to the varying number of neighbors. To estimate the performance of each onboard unit in the scenario in real time, we measure the number of neighbors located in each of the two clusters around each of the units. Our analysis of the indicators is derived from the sum of two values that are interpolated and extracted from the lookup tables. The estimated probabilities have an upper limit of 1. To measure the feasibility, we introduced another scenario. We assumed extremely congested traffic due to a highway repair. The traffic scenario is set to be 1,500-meter long highway. In this section of the road, there are 500 onboard units, which are equipped with V2X devices. Those figures represent the correlation coefficients for each performance metric, which evaluate the strength of the association between simulated and analytical results. The blue dots are distributed almost perfectly along the diagonal line, and the values are close to 1, which indicates strong correlation, demonstrating the effective estimation ability of the analytical model. To validate the model, we introduce a correction factor to eliminate error between the raw estimation and the realistic simulation results. After using the correction factors, the analytical model produces a very similar result as the simulation model. Furthermore, the lookup table can easily be adapted to the scenarios with different physics parameters. For example, different transmission power, just by recalculating the transmission and sensing range, since the contention mechanism due to CSMA stays the same. In conclusion, we select the 11p for the first version of intelligent fleet management. We proposed an analytical model which allows mobile working machines to have a real-time sense of network performance. We also published the research on 5G for the usage of large volume video streaming transmission for visual detection and segmentation. This paper is also available here. Even though the 5G has very high data rate and low latency, but it might be still not available on the construction site. In this way, our proposed analytical model can be used as a handover strategy in a hybrid network, where both Wi-Fi and cellular network are taken into consideration to combine the strengths of each network and minimize their weakness. Our vision is to realize an intelligent, connected, big data-driven construction site. Thank you for your attention.